Hello students, today we will discuss about JEE Mains 2015 physics paper. Now we will discuss all the questions one by one. Okay, let us start. Students, let us move to the next question. The question is two long current carrying thin wires, both with current I, are held by insulating threads of length L. So there must be a so the situation is like this: two current carrying wires like this, and they are held with threads like that, like this. You can see the diagram is these are the threads, which is like this. They are the two conductors which carries the current in the carries current of I, and these threads are insulating. So this is the situation. So that means in the paper the current is like this. The conductor is like this, and the current is either moving up or moving down. Here also the conductor is like this, the current is moving up or moving down in whatever direction it is. Now, so basically these are the conductors or wires which carries current I, is given I and I, same current, both with current I, and this is the suspended with this support with the angle. So the angle is theta. Okay, it makes an angle theta with the vertical. This also makes an angle theta with the vertical, and are in equilibrium. So once current is flowing, they will repel or they may attract. If the currents are in the same direction, they will attract. If the currents are in opposite direction, they will repel. So it is not mentioned whether the current are in the same direction or opposite direction, because they are maintaining some separations. That means the current are in opposite directions. When the current are in opposite directions, they attract. So they repel. Therefore, they repel, this conductor repels this conductor, so they maintain certain distance, and a particular position they are in equilibrium. So this position zone is the equilibrium position. With threads making an angle theta, with the vertical, if wires have mass lambda per unit length, wires have mass. Which wire? Is not talking about the thread. It's talking about the conducting wire. Its mass is not m, it has been given in terms of mass per unit length, that is given in the form of lambda. So then the value of I is, what is the current that is flowing in both the wires? G is a gravitational acceleration. Now let us draw the free body diagram when they are in equilibrium. So when they are in equilibrium, so the forces must balance out each other. So let us draw the free body diagram. Now I will draw the diagram. This is the wire, this is the ridge support. Okay, this is the vertical line, this length is L, this angle is theta. Now this will repel this in this direction, this is the force with which it will repel. This conductor will repel this conductor in this direction. There must be some tension in the thread, suppose this is T, and there is a weight which is moving down. Weight is m into g. Here it is the mass per unit length is lambda, so no problem, it's lambda into g. It should be m into g, but because it's given in terms of mass per length, so you can write lambda into z. Okay, mass per length. Per unit length, this is the mass. So, but this basically is the mass. Lambda g or into some L I can do, whatever is the length of this, I can multiply that. I can also multiply that, but finally they will cancel out, so I'm not writing that. Here it is whatever is the mass also, that is lambda g into T. Now what I'll do, I will first, if this is in equilibrium, then the net force on this will be 0. When a net force is 0 for this wire or this wire, suppose I'm talking about this wire, so for this to be in equilibrium, I can talk about this also. I'm now talking about this. For this to be in equilibrium, the net force on this should be equal to 0. Now you can resolve this T into two components. This component is T, because this is theta, so this will be theta. So this is T cos theta, and this component will be T sin theta. Okay, because you can see this line and this line, these are parallel lines, and this is a line which is connecting both the lines. If this angle is theta, this will be theta. So if this is T, then this will be T cos theta and this will be T sin theta by resolving the tension forces. Now you can see that this T cos theta balances the lambda g value, the vertical forces will balance out. So from here I'll write that T cos theta equals to lambda g, and similarly this F or T sin theta must be equal to F. So if I divide these two equations 1 and 2, what I will have, I will divide 2 by 1, I will have sin theta by cos theta, dt will cancel out, is F divided by lambda into g. Okay, now now what I'll do, I have to write the force. If this conductor carries a current I, this also carries a conductor I, and if there are two conductors, we also know that if there are two conductors carries a current, suppose I1 and this is suppose I2, if they are separated by a distance x, then they exert forces on each other. Now they are in the same direction, so they will attract, but in this case they are in opposite direction. Whatever is the case, the force magnitude is given by 0 upon 4 pi 2 I1 I2 divided by x, where x is the distance of separation between the two conductors, and I1 and I2 are the corresponding currents flowing through this, and 0 upon 4 pi is a constant that we know. So if this is actually the force per unit length, this is the force per unit length is given by this. Okay, now now this force per unit length, if I talk about that, now in this situation these are the two conductors separated by the distance of x. This is x. If I say that this distance is x, suppose I say that this distance is x, then this distance will be 2x. The whole distance is 2x because this is x and this is x. Now I'll write this x in terms of L, because L is given to us, because in the question what is given is x. Here, see here, the question L is given. So we have to write this x in terms of L. If this is L, this is theta, this will be L cos theta, this line will be L cos theta, and this will be L sin theta. Okay, so x comes out to be L sin theta, and the I1 and I2 are same in the question, and this is I. So here I will write I square, I and I will I square. The force acting per length will come out to be mu 0 upon 4 pi 2 I square divided by x. Here x means it is 2x. X means it is 2x. Okay, this force per unit length. So from here what I will have is this 2 and this 2 will cancel out. Okay, I will just cancel this 2, and this will be mu 0 upon 4 pi I square upon x. Let me tell you one thing, this is force per unit length, so I'm just writing F. This also means the force per unit length. Okay, and This is a force per unit length, so therefore this mass is also mass per unit length. So ultimately this will balance the equation. So I don't have to write that this is F by L is this or F is this into L. If you do that, that also is okay. Here also lambda, then you write lambda into L. So in both the cases it will cancel out each other. That you must understand, because this is mass per length. If L is the total length, then L you have to multiply. So this L I am not writing here, and this L I am not writing here as well for this force. Okay, so that will cancel out. So now let us move and substitute this value of F as this here. Again I am repeating that this F is here. Actually this is force per length, because this is M. Actually this should be lambda into L. You must not get confused with the dimensions. Let me explain to you this first. In most of the solutions you'll find that they take lambda g. So there is a logic to why they are taking lambda g, because we want to write the weight of this as mass into g. If it is mass into g, okay, then this would be mass is what? This is not the mass per length. If they write mass per length, then the dimension will change into the length. So if I want to say, if you don't want to write that like this, then actually L is multiplied already here. Then only dimension is correct, but I'm not writing the L. If L is you're multiplying here, then that L will appear here. Okay, lambda L, and this F by L will become this. So what I'm writing is, I'm not writing L here, and I'm not writing F by L here also. So I'll just write F by L as this directly here. Okay, then we'll proceed. So now this will become tan theta sin theta by cos theta. F I will take from here, which is mu 0 upon 4 pi I square divided by x. And what is x? X comes out to be L sin theta. So this is L sin theta. Okay, this part is okay. Divided by lambda into g. Okay, next we'll solve this in the next place. So from here the question is to find I. So I will rearrange the equations. So before that I'll write the equation once more. Tan theta is mu 0 upon 4 pi. I'm just rewriting the equations. 4 pi I square upon L sin theta, and lambda g was divided to this. So from here you rearrange the equation. That means we're interested in I. So you take all the terms to the other side of the equations. So I square becomes 4 pi L sin theta lambda into g, again tan theta is there, divided by mu naught. Okay. Now if I solve this, this is 4 pi L sin theta lambda g. This tan theta I write as sin theta divided by cos theta. So mu naught cos theta. This is your I square. Then what is I? Under root of this. If I take the under root of what will nothing is going to cancel. So this 4 pi L sin theta lambda g sin theta divided by mu naught cos theta. Now let me check the option. If I see the options, then exactly no option is matching, so I have to rearrange the thing. Something you have to take outside if you want any of the three. So 4 come out of the root, it becomes 2. That is sin theta and sin theta, so sin theta will come out. So 2 sin theta comes out. So you see that this is 2 sin theta over here. Okay, so you can see here 2 sin theta is there. So 2 sin theta I took out and rewrite what is left inside. If this part goes and this 2 goes, then what is left is lambda pi lg. Lambda pi lg will remain inside, and divided by this term will remain mu naught cos of theta. If I see the option number 2, 2 sin theta under root of pi lambda gl divided by mu naught cos theta. So therefore this is the answer, and the option number 2 is correct. So what we did is actually that we applied the force between two parallel conductors, and we took the equilibrium of the conductor, and then balance the equation and dividing and then manipulating it to get whatever is asked, and that is to find I. Okay, thank you.